Radiation, akin to the legendary creatures from ancient tales, is often misunderstood due to its invisible nature. The unseen can instill greater fear in human minds than visible perils. You might say, but nuclear explosions and freezing winters aren't imaginary. Just like electricity, the taming of colossal power sources in the 19th and 20th centuries birthed some nightmarish outcomes. Some sights simply can't be forgotten. However, when dread or irrational phobias arise, assessing the true extent of danger becomes challenging. Even more concerning, widespread fear and misinformation about radiation can lead to neglecting real risks. Surprisingly, medical applications of radiation have caused background radiation exposure in the United States to double since 1980, with similar trends in other nations. In this segment, we'll explore the elementary science of radiation, touching on the discovery of particle or nuclear radiation and its versatile applications. Spoiler: it's more of an awe-inspiring tale than a dull scientific lecture. We'll navigate through innovative medical treatments that save innumerable lives each year, the emergence of nuclear fission and fusion, and yes, even atomic and thermonuclear weaponry. On our journey, we'll meet trailblazers in broadcasting, medicine, and physics, as well as the unsuspecting and less than innocent victims of early radiation research. Uncovering the contrasting outcomes of these individuals can help us all comprehend the real pros and cons of nuclear science. In this video, you'll discover how a mishap with charged electrons paved the way for radio, the valuable lessons ram testicles provided for cancer therapy. Instances where even scientists perceive non-existent phenomena, driven by their intense desire for their hypotheses to be true. By Jove, I've witnessed the light. Such a humble phrase, yet it uncovers the almost magical significance of light in human lives. Be it sunsets or glittering water reflections, light, and the hues that result from its refraction, captivate us. These rays of light? Simply put, they're radiation. Indeed, it's the kind of radiation that tickles your retina's special molecules, making it visible to the naked eye. Positioned snugly in the center of the energy spectrum, visible light is flanked by infrared and ultraviolet energies. Just like all radiation, light is energy in motion, and it surfs on waves. From the lengthiest radio waves down the spectrum to the tiniest gamma rays atop the spectrum, all are merely energy traversing space. Einstein granted us the knowledge that all electromagnetic radiation sojourns at a consistent pace, the speed of light. Yet, akin to ocean waves, the peaks of these waves may be tightly clustered or spread out. Short, frequent waves bear more energy at the same velocity, whereas slow, undulating waves bear less. Electricity, too, is a nomad of energy. Once a destructive natural force, it now powers almost everything. Before the 19th century, lightning ignited fires and claimed lives in a flash. As electric light made its way into homes, it was deemed perilous, ironically more so than the gas lamps and candles that routinely incinerated dwellings. Radio wave discovery and early transmission, curiously enough, didn't evoke the same trepidation, despite their connection to electricity. Guglielmo Marconi, an ambitious 20-year-old, stumbled upon Heinrich Hertz's work, who had identified radio waves in 1888 within his lab. Hertz's discovery went largely overlooked, but upon his death in 1894, the press praised his work, and Marconi grasped its potential. Eagerly, Marconi embarked on a journey to investigate the prospect of employing long-wavelength electromagnetic, or radio waves for wireless message transmission. The key to unlocking radio communications, however, lay in a 1891 discovery by French scientist Edouard Branly. Picture this. Branly, experimenting with electric sparks, observes that the sparks cause metal filings sealed in a nearby glass tube to leap and align from end to end. When the electricity ceased, a gentle tap on the tube caused the filings to collapse once more. A mysterious force enabled them to defy gravity and arrange themselves in a straight line. What could it be? The force was so potent it functioned even when the spark was across the room. Before long, every scientist with a sealed tube of metal filings was testing this phenomenon. Better still, they found that by placing a bell adjacent to the tube, the filings could nudge the glass and strike the bell as they leaped. It didn't take long for scientists to amaze their peers by ringing a bell with a spark from another room, demonstrating that energy could travel through seemingly empty space. Marconi envisioned the potential to use electrical energy to extend wave transmissions. On December 12, 1901, he triumphantly transmitted a signal from Poldhu, England, to St. John, Canada. In the following decades, radio receivers became commonplace in households. Intriguingly, throughout this process, Marconi and his team never fretted over potential radio wave exposure hazards, despite knowing that energy waves could pose dangers. The electricity they harnessed frightened them, but the radio waves never did. Reflecting on this, Marconi himself acknowledged their lack of concern may have been short-sighted, but history ultimately proved him right. Why, you ask? The answer lies in wavelength, which we'll delve into now. 'Twas a fateful Yuletide in 1895, when German professor Wilhelm Conrad Röntgen found himself in a state of unease. Mere days prior, he had stumbled upon a mind-boggling discovery, yet it was so disconcerting that he wished it to be an error. His finding? Invisible rays could penetrate solid matter. Even with the evidence before his eyes, doubt clouded his mind. Unknown to Röntgen or other scientists of the time, Hermann von Helmholtz, a fellow German researcher, had predicted in 1893 that if rays with wavelengths shorter than visible light existed, they could traverse objects. Had Röntgen known this, perhaps he could have savored his holiday in peace. A firm believer in the power of relentless experimentation, Röntgen, on a day not long before Christmas, noticed that as he toyed with electricity on one side of the room, his fluorescent screen across the room emitted an eerie glow. Coated with a fluorescent compound, the screen seemed to react to the electricity from afar, leaving Röntgen perplexed. These enigmatic rays could not be bent using a prism, nor could their impact be impeded by placing an object between the source and screen, unless the barrier was metallic. Wood appeared transparent to these mysterious rays, but coins and other metal objects were not. Borrowing from the mathematician's vernacular, he dubbed them X-rays, signifying the unknown. Intrigued, Röntgen began placing coins in wooden boxes, marveling as the rays traveled from the spark, through the wood, and onto his screen. During one such experiment, his hand inadvertently obstructed the beam, and the sight that greeted him on the screen left him flabbergasted, the bones within his hand. Flesh didn't seem to hinder these newfound X-rays, but his hand's bones did. Days later, he confided in his wife, escorting her to the laboratory to showcase his findings. She too was amazed and a tad apprehensive about the revelation. Fortuitously, once Röntgen's confidence in his discovery solidified, he recognized its potential for medical advancement. Wasting no time, he published his methods and disseminated a handful of images, ensuring that every scientist or physician could replicate his results. A mere few months later, a successful surgery was performed to extract a bullet lodged near a patient's leg bone after employing an X-ray to pinpoint its location. The patient was spared amputation, and thus, the era of medical X-rays commenced. Serendipitously, Röntgen had shielded himself from these mysterious rays from the outset. Whether it was due to his prudent nature or the ominous sight of bones on a fluorescent screen, he remained unharmed. However, not everyone exhibited such caution. American inventor and businessman Thomas Edison eagerly embarked on X-ray experiments within his commercial laboratory. Edison's ruthless pursuit of bringing electric light to households placed him at the vanguard of innovation. Regrettably, it was these novel experiments that exposed the dangers of X-ray exposure. Edison's assistant, Clarence Daly, willingly subjected his hands to repeated X-ray bombardment to demonstrate the technology. Hand ulcers revealed the skin-burning potential of high exposure, but these ulcers soon turned cancerous, spreading from his hands, up his arms, to his chest, and ultimately leading to his demise. This brings us back to the subject of energy waves. Recall that shorter, faster waves carry more energy, while longer, slower waves carry less. It eventually became clear that wavelengths longer than visible light, such as radio waves, microwaves, and infrared, are generally safe. Conversely, wavelengths shorter than visible light, like ultraviolet, X-rays, and gamma rays, carry so much energy that they disrupt atoms and living cells. Gamma rays possess enough energy to strip particles from other atoms' nuclei as they pass through. Scientists refer to this as ionizing radiation, as ionization involves altering an atom's electrical charge by removing particles. Molecules lacking either electrons or protons are called ions, and their unbalanced charge tends to be unstable, leading to further breakdowns. These chain reactions in cells can cause mutations and even cell death. Thus, Marconi's lack of concern for radio waves was justified, as they posed no harm to him or his colleagues. Meanwhile, Edison, who was well aware of electricity's risks, mistakenly assumed that wavelengths shorter than visible light were equally safe. Edison himself nearly lost his eyesight after excessive observations. But as we will explore in upcoming chapters, the price of scientific discovery would prove even steeper for others. The uncovering of new energy wavelengths coincided with other remarkable discoveries. In France, scientist Antoine Becquerel found himself captivated by Röntgen's work, but more intrigued by fluorescence, the phenomenon of light-emitting chemicals. Combining his love for photography, Becquerel endeavored to capture fluorescence on film as if it were light. He sealed films in dark covers and dusted them with minerals coated in fluorescent chemicals, assuming that fluorescence, like X-rays, could pass through the covering and expose the film. Unfortunately, none of his fluorescence experiments succeeded until he tested the mineral uranium. Without light exposure but with uranium exposure, the photographic films revealed images even in the absence of light. Strangely, the uranium hadn't been treated with fluorescent chemicals. It seemed to emit a yet-to-be-discovered type of ray. In 1903, Becquerel shared the Nobel Prize for this groundbreaking discovery with the renowned scientific duo Marie and Pierre Curie. So, what was this new type of ray? Finally, we arrive at the topic most commonly associated with the present discussion: particle radiation, also known as nuclear radiation. Why nuclear? This term refers to an atom's nucleus or center, making it helpful to review basic atomic structure at this point. Atoms are essentially clusters of smaller particles organized by charge. The center, or nucleus, carries a positive charge, which comes from the protons it houses. Electrons, negatively charged particles, orbit the nucleus like planets around a sun. Neutrons, neutral particles with no charge, maintain stability within the nucleus. In large atoms like uranium, 92 protons, or radium, 88 protons, the positive charge within the nucleus accumulates, despite neutrons' efforts to maintain balance. Occasionally a particle is ejected, causing the atom to spontaneously decay into another state. During this process, the particle carries energy, and energy waves are produced. The ionizing radiation mentioned earlier is dangerous because it has enough energy to strip particles from an atom, leaving it unstable. For DNA and other complex molecules, this poses a significant threat. However, it is the ability to kill cells with higher wavelengths of particles, or nuclear radiation, that has introduced beneficial treatments to Western medicine. The controlled application of nuclear radiation in medical treatments, such as radiotherapy, has proven valuable in combating cancerous cells. By targeting specific areas affected by cancer, doctors can destroy or damage cancer cells, preventing or slowing their growth and reproduction. While it is true that ionizing radiation can be harmful, its controlled and targeted use has provided a valuable tool in the fight against many life-threatening diseases. So, as we have seen, the exploration of energy waves and their potential applications has brought about both immense benefits and substantial risks. The development of new technologies, such as X-ray machines and radiotherapy, has revolutionized medicine, while the understanding of the dangers associated with various types of radiation has led to the implementation of safety measures to protect both researchers and the public. The journey through the world of energy waves is a testament to human curiosity, ingenuity, and the continuous quest for a better understanding of the universe around us. You'll never guess what happened next. Our tale takes us to the Manhattan Project during World War II. This top-secret military research endeavor was born out of fear that Germany might be working on a nuclear weapon. scientists from the United States and its allies joined forces to develop the first atomic bomb before the enemy could do so. The Manhattan Project brought together some of the brightest minds in physics and chemistry, including J. Robert Oppenheimer, Enrico Fermi, and Niels Bohr, among others. These scientists began to apply their knowledge of fission and fusion to create the most destructive force known to humankind. The project was shrouded in secrecy, and the public was kept in the dark about the true nature of the research taking place. When the first atomic bomb was tested in the New Mexico desert in July 1945, it was a sobering moment for the scientists involved. The sheer power of the explosion was a testament to the incredible energy hidden within the atomic nucleus. As World War II drew to a close, atomic bombs were dropped on the Japanese cities of Hiroshima and Nagasaki, causing unprecedented devastation and loss of life. These events marked a turning point in human history and brought the war to an end. But the use of nuclear weapons also ushered in a new age of anxiety and uncertainty, as the world grappled with the implications of this new, terrible power. While the development of nuclear weapons is undoubtedly one of the darkest chapters in the history of science, it's important to remember that the study of energy waves and nuclear radiation has also led to many important breakthroughs and benefits for humanity in fields such as medicine, energy production, and space exploration. Radiation therapy has become an essential tool in the battle against cancer, saving countless lives by targeting and destroying cancerous cells while leaving healthy tissue relatively unharmed. In addition to X-rays, other forms of radiation, such as gamma rays and proton beams, are now used in medical treatments for a variety of conditions. Moreover, nuclear power has become a crucial source of electricity for many countries around the world. Despite the risks associated with nuclear reactors, such as meltdowns and the disposal of nuclear waste, nuclear energy remains an attractive option due to its low greenhouse gas emissions and the ability to produce large amounts of energy from small amounts of fuel. Many countries are now investing in new nuclear power plants and researching advanced reactor designs to improve safety and efficiency. Furthermore, the study of energy waves has also played a vital role in our understanding of the universe and our place within it. The discovery of cosmic microwave background radiation, a relic from the early universe, has provided valuable insights into the origins and evolution of the cosmos. Additionally, the detection of gravitational waves, ripples in space-time caused by massive objects like colliding black holes or neutron stars, has opened up a whole new way of observing and understanding the universe. While the story of energy waves and nuclear radiation has its dark moments, it also showcases the incredible power of human curiosity, ingenuity, and our capacity to harness the forces of nature for the betterment of humankind. As we continue to learn and grow, we must be mindful of the lessons from our past and strive to use our knowledge responsibly, always seeking to improve and protect the world we live in. And so, the story of energy waves, nuclear radiation, and human curiosity takes a dark turn. But as with every tale, there is light to be found in the darkness. The tragic events of Hiroshima and Nagasaki spurred international cooperation and efforts to understand and control the devastating power of nuclear weapons. The desire to prevent another such tragedy led to treaties, arms reduction agreements, and nuclear safeguards that, while not perfect, have helped preserve a fragile peace. Meanwhile, the knowledge gained from these events has also led to advancements in fields like radiation protection, nuclear energy, and cancer treatments. Understanding the effects of radiation on the human body has allowed for the development of more targeted and effective therapies that can minimize collateral damage to healthy tissue while maximizing the destruction of cancerous cells. The realm of energy waves has also continued to expand, with the detection of gravitational waves revolutionizing our understanding of the universe, and radio waves and microwaves playing pivotal roles in modern communication technologies. As we continue to explore and understand the natural forces around us, we are reminded that with great power comes great responsibility. Today, we stand at the crossroads of scientific advancement and ethical responsibility. The story of energy waves, from Marconi's radio waves to the atomic bomb, serves as a reminder of the duality of human discovery, its potential for both destruction and healing. As we continue to push the boundaries of our knowledge, it is essential that we strive to use these discoveries for the betterment of humanity and the preservation of our world. The future of energy waves and their applications is bright and full of potential. From harnessing renewable energy sources like solar and wind, to exploring the possibilities of fusion power, and even venturing into the realm of quantum mechanics, we will continue to uncover new aspects of these invisible yet powerful forces. In the medical field, advancements in radiation therapy, imaging techniques, and the development of new diagnostic tools will continue to improve patient outcomes and revolutionize healthcare. Our ability to manipulate and control energy waves will only grow, and with it, our power to positively impact the world around us. As we delve further into the mysteries of energy waves and their applications, we must remember the lessons of the past and act with wisdom and care. We have seen the incredible power of these forces, both in their capacity for destruction and their potential for healing. In the end, the choice is ours: to wield the knowledge we gain with responsibility and compassion, or to disregard the consequences and risk repeating the mistakes of history. The story of energy waves is a testament to human ingenuity, curiosity, and resilience. It is a reminder that even in the face of adversity and tragedy, we can learn and grow, using our discoveries to build a better future for generations to come. Thank you for watching this video to the end. We really need to get 1,000 subscribers, so it would really help us out if you would subscribe. You can also check out our other videos on the channel. See you soon.